Hello everyone, I'm Yoshihiro Shimomura from Design Research Institute, Chiba University, Japan. Thank you, Dr. Fang, for inviting me to such a valuable forum, the Fourth Scientific Design International Forum. This is my big opportunity to make presentation in front of you. Today, I would like to talk about the driving force, ergonomics for product design. This is the position of ergonomics. Ergonomics stems from occupational health. As with other areas of preventive medicine, the ultimate goal is to improve people's health. Ergonomics has uniqueness in that process. To improve the performance and well-being of people and organizations, ergonomics takes the methodology of scientific design. We do not just think about humans only, and do not just think about machines only too. Yes, we think human and machine should be unified as one system for development from the viewpoint of human science. This is the concept of human error. Ergonomists say that human error is not the cause of incidents. Human error is the result, and there is a different cause. Although the actions performed by humans are the same as shown in this figure, errors may or may not occur if the environment is different. The opposite is also true. Even if the environment is the same, if people change due to fatigue or learning, how error occur will change. In other words, human error is determined by the interaction between humans and environment. This idea is unique to ergonomics. Ergonomics has another concept. This is what robotics surgery looks like. Here, there is many interaction between robot and humans. Robots alone cannot perform surgery, and humans alone cannot do surgery either. When you look at this image as a human who uses a robot, there are many things that you can see for the first time. We call the situation like this systems approach. Approaching the system can reveal the problem. Then you can set goals and the challenges becomes clear. For example, we can see that this system is supported by the big effort and the isolation of the surgeon here in performing a precision task. I'm worried whether the surgeon's well-being will be fine if he continues to be such a stressful state. We have to think the system, including the robot and the human. This is a sample of early ergonomics. Old aircraft instruments were designed like this. Here, gears interlock behind the dial and automated directions of rotation. The dials read 8,808, but it is difficult to understand. As a result of research, here, the design of the instrument transformed into like this. The pilot can grasp the altitude at a glance by displaying large digits as numbers and using continuous analog needles for small digits. And here, conversely, this panel shows the initial design of the driver's seat for the Tokaido Shinkansen. Ergonomics is useful in designing unknown things that have never existed before. In addition to the size of the human body, the instruments and the operation method were designed according to the characteristics of human cognition. Furthermore, there was another important design, and it was so impressive for me. Despite the fact that autonomous driving was possible at that time, ergonomists equipped the console with a manual speed controller here. Manual speed controller. This improves the driver's sense of responsibility and motivation, performance of the system, and well-being of the individual. It's a great achievement of ergonomics. And next, modern ergonomics. The dashcam. Dashcam is a system created mainly by ergonomics researchers. In driving, there is no average. All events are variable, transient, and non-reproducible. Therefore, from the beginning of the development of dashcam, ergonomists insisted that driving should be recorded as an image. Next, the National Institute of Advanced Industrial Science and Technology in Japan has been conducting cutting-edge researches on human augmentation. By integrating technologies such as sensors and robotics with human physiological characteristics, new technologies are developed and new social services and lifestyles are proposed. And another one. Ergonomics has significantly permeated our lives. Stiff neck and stiff shoulder is a life disaster for Japanese people. Not only Japanese people, but also Asian people and recently worldwide. Is not an exaggeration. This photo was taken at the fashion event to raise social awareness on stiff neck and stiff shoulder. Ergonomics can also be introduced at such event. And next, the International Ergonomics Association has issued such recommendations at the height of COVID-19. This is an easy-to-understand illustration that introduces specific methods for healthy remote work and learning setup. Certainly, the evidence is also mentioned in this material. Originally in English, it has been translated in Japanese, Chinese, Malaysian, Thai, and other many languages. Here, let us think about actual methodology in ergonomics. First, usability from cognitive psychology point of view. This graph shows the result of a survey about mental models. Even if the same object is presented to subjects, the usage is different. Manipulation such as by adding a little knob like this to an object may or may not result to change. It is very complicated. There is no reproducibility. Users, including designer's mental model, is just one of the variations. And here, how do you move the adjuster when you turn the car's headlamps up, please think about this problem. How do you move the adjuster, this dial, when you turn the car's headlamps up? You may move it down, I think. However, that is because you are people from engineering field. When people with mechanical knowledge see a dial such as this, they unconsciously think of the axis of rotation. As a result, there are those who make mistakes and those who do not mistakes. There exists very big variance. And this one. Have you ever pressed the elevator open close button by mistake? This is an human error caused by the misarrangement of the visual movement direction of the door and the position of the operating button. This is the controllers of power window in vehicle. Operation tools like these samples that easily cause mistakes exist worldwide. Very many operation tools that may make the mistake. Certainly, please focus on the things you use in your daily life from the perspective of mental models and affordance. Next slide. Let us think about the ease of use from a kinematic point of view. A cup that is easy to hold like this is tapered so that the frictional component force reduces the burden of gripping. However, with a cup that is difficult to hold like this, if you apply too much force, the cup will fall, and if you put too little force, of course it will fall. It's very difficult to grasp. In this case, unconsciously you struggle on fine-tuning your muscles, and it will lead burden unconsciously. And here, a grip that exactly fits to the shape of fingers will not fit most people. In general, the size of hands varies very wide, so the viewpoint of mechanism and shapes is more important than the size fitting. And another example, high-end audio amplifiers sometimes have heavy volume knobs. By making it heavy, contraction of agonist and antagonist muscles is reduced, and the resultant burden is reduced. And another one, have you ever felt that something was difficult to use even though it was easy to hold? This is because the tactile sensation, tactile sensation is easy to detect, and the sense of force is difficult to be conscious of. Thus, hint for usability lies in considering unconscious responses of a human. Next slide. Usability is a typical endpoint in ergonomics. For example, usability can be high when task performance is high, biological burden is low, and the subjective positive feeling is high. With more learning, the effectiveness, efficiency, and satisfaction metrics change rapidly. Ergonomics is gradually permeating the field of product design with these objective concepts. And this slide shows how to measure the biometrics in usability. In addition to the multifunction system measured using electrical and mechanical methods, the central nervous system, circulatory system, and thermoregulatory system, sensory system, and so on, are also measured using electrophysiology or optical methods and various engineering methods. For subjective evaluation, in addition to the well-known best method, visual analog scale method, standard methods such as NASA TLX, NASA task load index for workload, and POMS for mood state are often used. And next, this is an example of an ergonomic design process. Feed-forward type design based on prototyping by expert review and feedback by usability test are repeated. These are performed as necessary in each phase of planning, development, and quality assurance. In the experiment, we will comply with each guideline and basically use a protocol that has been approved by ethical review committee. And here we are going to samples. This is an example of a medical product, an expert intervening in the design of the device that simultaneously filters, concentrates, and re-injects ascites. The device is used in a narrow space at the patient's bedside. It was designed to be easy for medical professionals to operate and make it difficult for patients to feel negative emotions such as fear. We're going to next. This is a human-machine interface vehicle. Adaptive Cruise Control (ACC) is a system that allows the vehicle to travel at a set speed while maintaining a constant minimum distance from the vehicle in front. In such automated driving system, it is important to intuitively recognize whether operating authority belongs to the machine or the human. Steering wheel, pedals, and other controllers must be systematized and integrated with the human body. We have developed in this design project an interface that controls ACC on/off by side tilting. This is a prototype model, a side tilting lever. Here, this is the speed control knob equipped on the steering wheel. And this is physically links it to the pedal status, axle and brake pedals. And next, this is also medical tools. Manual devices for peritoneal dialysis that patients use at home have been very difficult to use. We made them easy to use with just one attachment. We analyzed the tasks from the tube connection to end processing and integrated the assist functions in each process into one attachment handle. This is the first sketch of the handle. From the result of usability test experiment, muscle strain reduction of up to 19% was recognized. In this experiment, we used 3D printing models, and we fed back the evaluation experiment results to the design and decided final product. And this is the final sample in this presentation. Measuring tapes are widely used to measure the circumference of limbs, upper limb and lower limb. However, the inability to control the quality of medical staff's skill was a major problem. This is here. I have a real product here. A calf circumference measuring tape for malnutrition screening in the older adult was designed by expert review. This design provides orthogonal with the tibia and unconscious tension control. The result was published in the Japanese Journal of Ergonomics. This data is from that article. The misjudgment rate here, the misjudgment rate and the intra and inter-individual errors were significantly reduced as a result of the usability test. Furthermore, the measurement time has also been decreased. Through ergonomics, product design with high usability was created, reducing the risk of misjudgment in this project. Ergonomics seems to provide goals and methods for product design, as in the cases we have discussed above. We ergonomists will contribute to the well-being and high performance in the life worldwide. I hope the ergonomics will contribute to the design field more and more in the future. Thank you very much.